we shall wrap up this discussion on the ideal Bose gas, but before that let us discuss a few relevant things which are namely the discontinuity of the specific heat across Tc. While I thought that this could be a part of a tutorial, but then I thought that it involves quite intricate calculations. So, let me at least show the steps. Then we will talk about the summary and some experimental aspects of BEC, and then finally we will do black body radiation, which is derivation of Stephan's law, and finally the sound waves or the specific heat due to phonons. Okay. So, discontinuity in specific heat. So, we will show that the specific heat undergoes a discontinuity at T equal to TCO or across the transition, and for that we will have to take the full expression for the specific heat that we have taken or rather derived yesterday, and it was this G 5 by 2 ZF divided by G 3 by 2 ZF and minus 9 over 4 G 3 by 2 ZF and G half ZF. And this is the expression for complete expression for specific heat. This is valid at large temperature as well as very small temperature below Tc and at Tc. Is just the this behavior of these G functions or the Bose-Einstein integrals. They change. In fact, between 0 and Tc they are independent of ZF, where ZF is close to 1. Now, at large temperatures they in fact fall off, which is what we have shown. So, for T less than Tc, we have Cv equal to 15 over 4 Nk T over Tc whole to the power 3 by 2, and then we have this zeta 5 by 2 and zeta 3 by 2. So, if you call this as equation 1 and this as equation 2. So, this is the specific heat where we have put ZF equal to 1, and then hence we have sort of substituted all these expressions, and remember that the last one, that is G half at 1 is infinity. So, the last term drops out and one has this form for this the temperature dependence as going as T to the power 3 by 2. So, above Tc, of course, it is still given by this equation 1, and for the explicit temperature dependence for temperatures above Tc, we need to solve this equation. Okay. Now, for that what we need is that we need some virial expansion of these G 3 by 2 and 5 by 2, which are there in part 3. I will not go into details of that. Rather, we will write down these expressions which are the expansions of these virial expansions of this Bose-Einstein integral, which is gamma minus half root over of ZF plus zeta of 3 by 2. So, we are just trying to calculate for T greater than Tc. In fact, what we are interested in is that T equal to Tc plus, which means just above Tc, and these are the expansions or the expressions that would be used, and this is a minus 3 by 2 ZF to the power 3 by 2, and then we have a minus ZF minus of ZF, and then we have this as 3 by 2. Okay. So, let us call this equation as 3a and 3b. The proof of these are not given here, but they are like this virial expansion of the BE integrals. Okay. So, if we get this, or say it is given to you, and then we have to just keep in mind that gamma half is equal to minus 2 root pi and a gamma 3 by 2, or rather minus 3 by 2, is equal to 4 root pi by 3. And these are all what are needed for us to calculate the specific heat for T just greater than T c. So, what we get is the following. So, for T greater than T c, T is equal to T c plus, say for example, and this is equal to n over V lambda cube is equal to. So, this I write down the number equation. So, that is the number equation. So, n by V into lambda cube equal to G 3 by 2 ZF, and this is equal to gamma minus half root over of ZF and plus of the zeta 3 by 2. So, now we can find out this equation to get ZF, that is the fugacity, and we have actually plotted the this fugacity variation of fugacity with temperature, and this is given by the root over of ZF equal to this zeta 3 by 2 divided by 2 root over of pi, and we have 1 minus T c over T whole to the power 3 by 2. So, that is the expression that we have. So, we can term this as 4 and this as 5. So, that is the expression for fugacity. So, now we will use, in order to get the discontinuity at T c, we will use the U expression, which is nothing but 3 by 2 N k T G 5 by 2 ZF divided by G 3 by 2 ZF. So, the last part that we did, that is calculation of this ZF. So, one gets the expression for ZF as a function of T, which we have plotted earlier, but we have not derived an explicit expression. So, this gives you an explicit expression for this. Zeta 3 by 2 is constant, it is a known value, and then everything else is a known value. So, this is T c by T or T by T c, it behaves like this. Okay. So, now we can use this expression for these ratio of the two Bose-Einstein integrals as this is G 5 by 2 ZF by G 3 by 2 ZF is equal to this 5 by 2 divided by 3 by 2 plus 2 zeta of 5 by 2 root over pi ZF, and then we have this 3 by 2 whole square. So, this is square of that, and plus 4 5 by 2 pi by 3 by 2 whole square minus zeta of 3 by 2 divided by zeta of 3 by 2, and we have a ZF here. So, we can write a ZF here. Okay. So, that is the expression for this ratio that you see there, and once we get this ratio, let us call it as equation 7, and we can put it in equation 6 here. So, we can put 7 in 6 in order to get U, and once we get U, we can actually eliminate ZF using 5 and 7. So, put ZF from 5 in equation 7, then you do not see a ZF there, and then you can put it back into, and then put it back into equation 6. Okay. So, that is the plan, and then you can take a temperature derivative, and this gives you a CV, which is equal to a Nk. You have 9 by 2 zeta 5 by 2 zeta 3 by 2 minus 3/8 zeta 3 by 2 whole square divided by pi plus 9 over 4 and zeta 5 by 2, zeta 3 by 2 minus 3 over 8, this is actually 8, 3 over 8 and you have zeta 3 by 2 square over pi, and this is with the Tc over T whole to the power 3 by 2 and plus a last term which is zeta 3 by 2 whole square divided by pi minus 3 zeta 5 by 2 divided by zeta 3 by 2 into Tc by T whole cube. The expression is quite long and it has obtained by taking a derivative of the internal energy that is written here in equation 6 and with all the substitutions of all these g 5 by 2, g 3 by 2 and then replacing Zf from there and then taking a time derivative there. So, basically this is the expression for Cv at T equal to Tc plus. Okay. So, this is just above Tc. So, that we need to know the discontinuity at Tc. Okay. So, del Cv del T and this is at T equal to Tc minus, which we have already found, that is the Tc minus. So, this is the Tc minus in equation 2 and the Tc plus is this equation, which let us call it as equation 8. This is equation 8 minus del Cv del T at T equal to Tc plus, this is equal to, if you do a simplification of all this becomes zeta 3 by 2 whole square divided by some 16 pi and Nk over Tc and whatever it is a constant. Okay. So, if you plug in all these values etc. So, if you simplify this number, this becomes 3.6658 into Nk over Tc. Okay. So, that is the discontinuity and so the specific heat is continuous across the transition, but the derivative of the specific heat is discontinuous, as it is clear from the kink that we have seen there. Okay. So, this just I mean it is not very important, but what it says is that in this particular case in spite of this being a second order phase transition, because we were able to define an order parameter which are the condensate densities and all that, we still have this specific heat to be a continuous and it does not involve any latent heat. The transition from a gaseous phase to a condensate phase does not involve a latent heat and hence it is a second order phase transition. All right. So, we will now do a little bit of summary of these things, that is the Bose-Einstein condensation, just to remind you of a few things that we have done, and we will also do the experimental aspects, but just do a bit of summary which we have done. It just it is very clear, though I would sort of state it anyway, that this is a condensation in the momentum space. So, k equal to 0 states are macroscopically occupied. Okay, which was very clear from the velocity plots that we have shown earlier, that at sort of Vx equal to 0 or Vy equal to 0 or whatever Vz equal to 0, it is in a two dimensional sense. The atomic density is really large for these kx equal to 0, ky equal to 0 or Vx equal to 0, Vy equal to 0 and so on. So, that tells you that these are the states that are macroscopically occupied, and this really is not a condensation that is seen in the real space, but it is in the momentum space. And of course, very importantly, the particles are non-interacting. So, if I go back to the way we started this studying Bose-Einstein condensation, you would remember that the density of states in 3D was going as epsilon to the power half, and we said that look, I mean epsilon equal to 0 comes with no weight at all or no density of states at all, which means that is it that it cannot handle particles in that state, but that is the most important state at low temperature. And hence, we have separated out the contribution of this epsilon equal to 0 state from the epsilon not equal to 0 state, and then we have done these discussions thereafter. Okay. So, with the premise that these are non-interacting particles, and this is given by this h cross square k square over 2m. And when we talk about epsilon equal to 0, we really talk about the k equal to 0 state that we are that shows this condensation phenomena. And of course, the helium 4 we have discussed that it came very close to the transition temperature is about it's like 3.13 Kelvin according to a Bose-Einstein condensate. If you put all these values of m, we have shown that, but the actual transition temperature is about 2.17 Kelvin and so on. Okay, it is close to that. So, which means that this only differ by a degree, and so what could be happening is the Bose-Einstein condensation in helium atoms, and it turned out that it is not as simple as that, because there are the interaction effects in helium atom cannot be ignored. In fact, they are quite strong. And because they are strong, this is not really a phenomena that can be ascribed or rather assigned as Bose-Einstein condensation. And later on Landau and Feynman and Tidza, they have worked a lot on these things, and then finally there was an outcome that this is a superfluid state which flows with if you put that helium atoms below that transition temperature, they lose all viscosity. So, if they flow into if there is a laminar flow through a tube, they would not stick to the walls of the tube. It is completely frictionless and viscosity less. That is kind of a state. Anyway, it is not a Bose-Einstein condensation. That was somewhat clear. Now, we are talking about Bose particles. So, what kind of particles are Bose particles? Are they there in nature and so on? Yes, they are there in nature. So, we are talking about actually bosonic atoms, and sometimes we can the common candidates can be say alkali atoms. Okay. They are monovalent ones, so they should have in principle fractional spins or half integer spins, and now that cannot be. Half integer spins are not bosons. So, what exactly are we looking for as bosonic particles that would undergo as Bose-Einstein condensation? Now, what can happen is that these atomic spins are, so F, let us call it as an atomic spin, and this atomic spins are combinations of say for example, the nuclear spin and J, which is the electronic spin. So, I am talking about the spin angular momentum, and F is equal to I plus J, and so F has a range from I plus J to I minus J. Okay, and the mod of that. Okay. So, now for this monovalent alkali atoms, such as for example rubidium, sodium, lithium, and all these things, etc. Okay. It was first seen in rubidium atoms. So, we have this J equal to nothing but S, angular the L is equal to 0 here is half, and we also have I equal to 3 by 2. So, F becomes equal to 1 or 2. Okay. So, this is the the atomic spin that we are talking about, and that is why they are bosons. Okay. But you understood that we had to combine the electronic spin and the nuclear spin, and the nuclear effects, for them to become comprehensible, or for them to show up in experiments, we really need the hyperfine scale to come into picture, which means that the temperature has to be extremely low. And because we want the temperature to be very low, of the order of as you saw, that of the order of 100 nanokelvin or so, it took a very long time for these condensates to be made and this Bose-Einstein condensation to be achieved. Okay. So, there are many techniques of cooling that one can actually think of, and though it is not a part of this statistical mechanics course, because those are cooling techniques and so on, and then there are a number of cooling such as, so let me just tell you a little bit. One is called as a magnetic evaporative cooling. And maybe the laser cooling, etc., and so on. And then this laser cooling actually won a Nobel Prize, this technique itself, for Stephen Chu, Cohen Tanoji, and Phillips. So, this you target two laser beams, counter propagating laser beams towards an atom, and the atom actually the momentum, effective momentum of the atom, the moving atom of course, that goes down, and you can actually slow down the atom significantly, and that would lead to the cooling phenomena. And this magnetic evaporative cooling can be done by using some anti-Helmholtz coil. So, what we mean is that if you remember this Helmholtz coil, where you have these currents moving in the same direction, and if you remember that there is the magnetic induction or the magnetic force, let me just draw a little. The magnetic force is the magnetic induction. So, this is the B that we are talking about, and B as a function of distance. So, this magnetic induction is pretty smooth, that is constant between the two these coils, or these two Helmholtz coils. Now, you can just make a sort of inverse of that, that is the currents are not moving in the same direction, but they are moving in opposite direction, in which case instead of this. So, I will just draw it a little here. If you make them move in two different directions, then you actually have just an inverse thing, where the constant thing does not come at the top, but it comes at the bottom, or and makes like a cup. So, you load these atoms in a cup, and these atoms are would escape depending on the trap height, and the more energetic atoms would escape, and leaving you with the less energetic atoms, or the cooler atoms, the atoms that are colder, and these would one of the cooling techniques that is used. And for example, laser cooling is used, little can be said about it, that so when there are this atom has a natural frequency omega naught. So, this is the natural frequency. What it means is that the energy levels are simply differ by h cross omega 0. The intrinsic energy levels of the atom, they differ by omega h cross omega 0, and omega is the EM radiation frequency, that is the laser light. Okay. So, if you put it in that, then the probability that it will absorb the radiation is given by, so this probability is given by this 1 by omega minus omega naught and a plus minus I gamma by 2, where gamma is it's called as a natural line width, or it is related to the lifetime of this atom, natural line width, basically the width of the spectral lines. And you know, now if you think of the atom to be moving, then the Doppler effects come into picture. So, if an atom is moving towards the laser source, then it will be, its frequency increases, and it's called blue shifted, and if it's moving away from the laser, then the frequency goes down, and it's called as a red shifted. It's just pretty similar to if you are moving towards a train, or and then the train is honking, the sound of the the horn, that would seem like either it's increased or decreased depending on whether you're moving towards the train or moving away from the train. A similar thing happens, but what importantly happens is that there is a frequency shift which is called as a Doppler frequency shift, which is of the form which is v dot k, where v is the velocity and k is the wave vector. And so eventually this denominator of this this probability of absorption, so this looks like omega minus omega naught minus a v dot k and then a plus minus I gamma by 2. Okay. This by 2 is just a convention, and so because of Doppler effect we see a detuning parameter, which is this detuning parameter is called as minus gamma plus gamma 0. So, if you define a delta prime which is equal to a delta plus this d omega, or this minus delta omega, so this becomes equal to delta plus v dot k. Okay. So, this is called as a detuning parameter and so on. So, this is the Doppler effect that comes. Now, if you have two counter propagating laser beams, then so one will have so for two of them, so you have one this Doppler shift will be equal to delta plus k v and so on, and for the other one you will have this delta minus k v and so on, and then there is a net reduction in momentum. So, reduction in momentum will be twice of that of the atom. Is twice of this k and v, and this means that the overall the momentum goes down, the kinetic energy goes down, and hence the temperature goes down. Okay. So, this is called as a laser cooling. As I said, that these are very important things, discoveries which had actually made this realization of Bose-Einstein condensates possible. Okay. Anyway, as I said that they are not really part of statistical mechanics course, but it's also good to know, because this ultra cold atoms and the physics of ultra cold atoms, they play a very important role in simulating many quantum phenomena. Okay. And there are these, this quantum sensing, quantum information, quantum information, there, I mean quantum computation, etc. They are emerging fields, and a lot of these important discoveries are linked to ion traps and these condensates, Bose-Einstein condensates, cold atomic traps of different geometries and so on. Okay. So, we shall stop here with this Bose-Einstein condensation and finish up two small topics in ideal Bose gas, and they are called as the black body radiation you might have studied it in your first quantum mechanics course, which actually, as I said earlier in one of the earlier lectures, that this is really the first time that it was felt that this classical theory or the semi-classical theory isn't working, and there has to be a new line of thought that would is required for this black body radiation to be explained. Okay. So, we are talking about a black body, and a black body means that there are three things. So, let us call it as a when an electromagnetic wave falls on a material, then three things can happen. That it is it's reflected with this amplitude, okay, and or it's transmitted with this amplitude t, or it is absorbed with amplitude a. So, this is when electromagnetic radiation falls on a black body, and what happens is that this r plus t plus a should be equal to 1 for the conservation principle, and for a black body, these all these two, both of them, so you have r equal to t equal to 0 and a equal to 1. So, this is called as it's perfectly absorbed, and that is why it is called as a black body. Okay. So, we are just simply talking about electromagnetic radiation or light and so on, whose energy versus momentum is given by E k equal to c into p, or it is written as h c and a k magnitude of that. So, you can simply write it as h cross c k. So, the one important difference between what we have done so far with Bose-Einstein condensation is that we had a k squared dispersion. So, these are non-relativistic particles, but these are the photons are ultra relativistic particles whose the dispersion is given by linear in k. And we also know that the chemical potential of photons are this is 0, chemical potential is equal to 0, and the reason we have stated earlier at least twice, saying that because the number of photons cannot be conserved, so we do not need a constraint condition linked to the number conservation, and that is why that particular Lagrange's undetermined multiplier equal to 0, and that is why mu is put equal to 0. So, we will not go into a lot of details, but we write from the grand canonical partition function as this, as we have started even working with your PV over KT. So, I am just writing the relevant part of it. So, PV over KT was linked to log Z. We have shown that how the grand potential is related to log Z and so on, Zg in the grand canonical ensemble, and this is log of 1 minus exponential minus of beta epsilon k, and this is equal to PV over KT. This is the starting point. We have said that a number of times. In fact, we started from this when we started dealing with the ideal Bose gas. Okay. That is PV over KT. Now, you have to convert this sum into an integral, but I leave that to you to figure out what is the density of states for a three-dimensional system whose dispersion is not k square. In k square, it was epsilon to the power half. You have to figure out what it is for this linear dispersion, and when you do that, you would get that this log of Zg is nothing but a minus of there is a minus sign. Yeah, I put that. So, minus 4 pi v divided by hc over whole cube, and is 0 to infinity d epsilon epsilon square log of 1 minus exponential minus beta epsilon. Okay. So, basically even here it does not cost any energy for a large arbitrary number of particles to be in the epsilon equal to 0 state, but this divergence of the epsilon equal to 0 state occupancy has got no effect on the physical properties for photons. So, there is nothing like a condensation phenomena that occurs for photons. Okay. So, this is nothing but if you try to solve this integral, you can do it by parts, and we have told number of times you should take epsilon square as the first function, log of this 1 minus exponential minus beta epsilon as the first function and epsilon square as the second function, and do a by parts integral, and it will give you a simple expression which is log of 1 minus exponential minus beta epsilon and epsilon cube by 3 from 0 to infinity, and you have the second term which is this du dv integral of v dx whole dx, that is exponential minus beta this and 1 minus exponential minus beta epsilon d epsilon and so on. Okay. And now this as earlier, this is equal to 0 because at the lower limit this term goes to 0, and at the upper limit, that is infinity, this log term goes to 0 because this term goes to 0 and log of 1 is 0. Okay. So, we are left with only this term, and that is simple to deal with because this would eventually give me a Bose-Einstein integral of with some argument which we should be able to figure out what it is. And so, this is equal to 0 to infinity, and this epsilon cube d epsilon and e to the power beta epsilon minus 1. Okay. So, this is the pressure, and we know how to calculate the internal energy, and the internal energy is nothing but this u at a constant t and v. This is nothing but k and epsilon k divided by e to the power beta epsilon k minus 1. Note that we have not written mu because mu is identically equal to 0. So, it is a 4 pi v divided by h c whole cube, and integral of 0 to infinity d epsilon epsilon cube e to the power beta epsilon minus 1. Now, you see the pressure expression and this expression are nearly same with just a factor of 1 over 3, and we have said this result before that you really have these u and p, that is the internal energy and the pressure, they carry the same information. So, p is equal to number times some number times u by v, and this number is equal to 1 by 3 for relativistic case and this is equal to 2 by 3 for non-relativistic case. Okay. So, that is all that you have. So, here we will write a 1 over 3. So, now with if you change x equal to beta epsilon, then log of zg at Tv, which is equal to Pv over kT, this is nothing but equal to 4 pi v by hc cube and 2 over beta cube and a G41, which is the Bose-Einstein integral. So, if you compare, you get this G41, and this just to remind you that this GNZF this is equal to 1 over gamma n, and you have a 0 to infinity x to the power n minus 1 dx and ZF inverse e to the power x minus 1. So, we can use the this G4 of 1, which is nothing but a gamma 4, which has a value pi 4 by 90. We have shown that earlier that this is just a value of the Bose-Einstein condensate. I mean the integral, sorry, not the Bose-Einstein. This is a Bose-Einstein integral, and this is u by v, which is 8 pi by hc cube, pi to the power 4 by 90 and a kT to the power 4, and this is called as the Stefan-Boltzmann law. Or more familiar of it, if you calculate the emissive power or the energy density of radiation, which is if you simply divide this quantity by the speed of light, you will get a E equal to some 4 by C sigma T to the power 4, and this is known as the Stefan-Boltzmann law, and this sigma is called as the Boltzmann, and sigma is called as the Stefan-Boltzmann constant. I will just write it in brief, and it has a value which is 5.67 into 10 to the power minus 8 watts per meter square Kelvin to the power 4. Okay. So, this is called as the Stefan-Boltzmann law, gives you the emissive power or emissive energy density associated with the electromagnetic radiation of a black body. Okay. Now, finally, we will talk about phonons or the specific heat due to phonons, or these are called as the sound waves, and these sound waves, because if you just to remind you that if you solve a diatomic chain problem, then what you get is that you get the acoustic modes as like this, and they will go as like this, and the optical modes are like this. So, this is the Brillouin zone pi over A and minus pi over A, and we are really interested in this region where these are called as the acoustic modes, because omega is proportional to k, or the frequency is proportional to k. Okay. And of course, Einstein did a mistake, and Einstein actually got a temperature dependence of the specific heat to be completely wrong. In fact, he got some quite complicated, is 1 over t square exponential minus 1 over t, that kind of a dependence. So, Einstein's result, I will not go through it. It was done when we did this harmonic oscillators, independent harmonic oscillators, calculated the partition function, calculated free energy, and then the specific heat. So, Einstein's formula or Einstein's result was wrong, because he assumed that all the this lattice points or all the ions are they are vibrating with the same natural frequency, which means here the model for a solid is that we have ions there and they are connected by springs. So, they would undergo harmonic vibration, either it can go in the plane or it can go above the plane, and in plane there are two modes, longitudinal and transverse, and then you have the out of plane movements, etc. Not longitudinal and transverse. So, in the plane you have one along x maybe and the one along y, that is what I meant. Okay. So, this result that Einstein got, I will not derive that, it was derived earlier. So, this was like a 3r and a theta E by T. There is a low temperature behavior. High temperature, both Einstein and Debye were correct that it goes as 3r, but there is no temperature dependence there. So, this is the thing that Einstein got, and theta E is some Einstein temperature, which is like this is like theta E is that h cross omega by k or something. Okay. So, this result is like 1 over t square into e to the power minus 1 over t. This is wrong, because experimentally it was found that the low temperature behavior is like t cube, okay, and this is called as a Debye's theory. So, we will just quickly do Debye's theory and be done with this ideal Bose gas. The important thing is that why does one need the specific heat? So, the experimentalist needs specific heat because it's a response, it's a linear response. So, if you increase the temperature by 1 degree, how much of heat is required? That is called as a specific heat. So, and this behavior of specific heat with temperature is an important thing. It shows phase transition. For example, this phase these superconductors, they show a drop or the discontinuity in specific heat and so on. And we have seen here also that the specific heat has a kink like structure at T equal to Tc. So, it is an important quantity, and you do it in solid state physics. So, I will not repeat it much, but I will simply say that you have this E to be like a Cs into P, and now the Cs is called as the speed of sound or velocity of sound. Okay. And of course, not light. So, Cv will be a del U del T at a constant V, and this is like a 3nk h cross omega beta square e to the power beta h cross omega e to the power beta h cross omega minus 1 square. So, this is the Cv that comes, and then you can take a low temperature limit and a high temperature limit. High temperature, as I said, will give you 3R, and the low temperature it will reproduce the T cube formula. So, the density of states for phonons. So, this Debye made a important contribution. It's a volume, and this omega square divided by 2 pi square CL cube. CL is the longitudinal velocity of this sound, and it's pi square CT cube. So, that is the density of states, and CL is the longitudinal speed of sound, CT is the transverse speed of sound, and has a cutoff at omega equal to omega d. And this is the mistake that Einstein made, where he assumed that all of them have one frequency. Okay. However, there is no it's not one frequency, but there is some frequency which has got a cutoff. Okay. I am showing only schematically. So, this g of omega has some cutoff there, where it is sort of the smooth function is written here like omega square, but with there are combination of two terms. Okay. So, this d is called as a Debye frequency. Okay. And when one actually integrates over omega d, one get 3n number of modes, and this is equal to 3n. That gives a Debye frequency to be equal to 18 pi square. So, if you solve this, put this g omega here and solve for this from 0 to omega d, or rather integrate from 0 to omega d and equate it to 3n, where 3n is a number of modes, phonon modes that we are talking about. Basically, the energies, the phonon energies are this many in 3 dimensions. So, this is 18 pi square n over v, and we have 1 over CL cube plus 2 over CT cube whole to the power inverse. Okay. So, now I know omega d. So, we can calculate u T V n. This is equal to 9 nh divided by omega d cube 0 to omega d d omega, and we have 1 by exponential beta h cross omega minus 1 plus half omega cube. So, g omega, putting the value of these, so this is 9 omega square by omega d cube. So, it is omega square variation for omega less than equal to omega d, and that is equal to 0 for omega greater than omega d. So, okay. So, C, the specific heat, is equal to del U del T and V n. This is equal to 9 n h cross square by omega d cube k t square. These are you have to do it once in order to convince yourself, and there is some omega d, and then there is omega to the power 4 exponential beta h cross omega divided by exponential beta h cross omega minus 1 whole square. And if you replace x equal to beta h cross omega, then what you get is you get a simplified form for this. in terms of an integral, and then one can actually have a exact form of the integral, and this is like a 0 to some x 0 dx x to the power 4 e to the power x divided by e to the power x minus 1 whole square. So, if you define a Debye function, d of x 0, which is this integral 2 divided by x 0 cube 0 to x 0 dx x to the power 4 e to the power x e to the power x minus 1 whole square with x 0 as h cross omega d by kt. So, one gets CV equal to 3 n k d of x 0. Okay. So, this is the form that one has, and at high T, that is at high temperature, d of x 0 is equal to 1. So, that gives CV equal to 3 n k or 3 r, and at low temperature or very low temperature, d of x 0 goes as t cube. So, this gives the CV going as t cube, which is correct, okay, and this is called as the Debye's theory. All right. So, we wind up our discussion on the study of ideal bosons, and we have done a number of things: Bose-Einstein condensation and its properties, that what happens when there is a macroscopic accumulation of particles in the ground state of the system. Then we have done these black body radiation and hence the phonons. We have done these phonons and black body radiations in hurry, because you already know that in the context of either quantum mechanics or solid state physics. So, the results are important nevertheless, but the condensation phenomena was new to you, and it is one of the main topics of discussion in statistical physics. I will stop here and we will carry on with discussions on Fermi systems in the next class. Thank you.